Here we go. So another lovely video which uses like de Moivre's theorem. Gee, that's messy. Really messy. I apologise for that. De Moivre's theorem. And if you remember, de Moivre's theorem is r cis theta. If it's raised to any power n, that's r to the power n cis n theta. We're going to make use of that. And what we're going to try to find is we're going to try to solve any z to the power n is equal to a, where a is any complex number. Okay, so it could be I, it could be 2 plus I, it could be 7. These are all complex numbers, and so we're looking for the solution to any of these sorts of things. When it's in this form, we're going to have a look at how to solve this, and an application of this is how to find the square roots of complex numbers and stuff like that. So a very interesting way to look at it. If you get an equation in this form, what will happen on the Argand diagram is that gee, that's bad. Sorry, you guys should sack me if you do that. That's not bad. Then what will happen is that all of your roots, let's say it was a z cubed equals I or something like that. What will happen if it's cubed? It means all of your roots will be divided up equally around here. So you get one there, maybe one there, and maybe one there. That's not very equal, is it? In fact, it's terrible. But what my main point is that they'll all be divided up equally by an equal angle all the way around the triangle. So it'll divide the Argand diagram into 3 equal pieces. Okay. If you have quarter, might be a bit easy. If you've got something like z to the quarter, z quarter equals 2 plus 6i or something like that, what will happen if your first root is there, then because it's going to divide it up into 4 equal pieces, your second root will be there, your third root will be there, and your fourth root, it's terrible again, but anyway, it divides it up into 4, so each of these will be 90 degrees. Okay. Fantastic. So that's how it works. If it was a a square root sort of thing, so z squared equals -9 or something like that, what you'll find is that if one of your solutions is there, because it divides the Argand diagram into 2 pieces, it'll just be opposite sort of thing. So that's what we're looking at. Let's do some examples. Okay. First example, let's just go straight into it. Z cubed equals I. Okay, let's have a look at this one. There's two ways to well, no, let's just do this the one way. Keep it simple. Best way is to let Z be equal to R cis theta. We're going to find it in polar form. It's the easiest way. And now let's rewrite it. So therefore, what we've got is R cis theta cubed. Okay, so the Z cubed is equal to I. Therefore, let's just open it out. R cubed cis 3 theta is equal to, now I just want to write I in polar form. How do you write I in polar form? Well, let's just think about it. I is up here, okay? And what will the angle be? Well, the angle for I will be what am I doing? It'll be pi on 2, okay? So it'll be cis pi on 2, so that's where I is, it's right on the axis there, pi on 2. And what's the radius there? Well, I is 1 up there, so the distance, the modulus will be 1 from there. So 1 cis pi on 2. So it's good to know what numbers, different ways that what they translate into in polar form. Okay, so now that we've got this written like this, what we can do is we can look at r's there, and we can look at our angles there. So our modulus and our angle, and we can just equate each part. So therefore, what we have is we've got r cubed must be equal to 1, and moduluses must be the same. Okay, and r is always positive, therefore r is equal to 1. And modulus of our solution, z, is equal to 1. Let's equate our angles here, and also 3 theta will be equal to pi on 2. Okay, now pi on 2 is our first argument, but really it could go around and around and around and around. So what we just need, and this is how you need to be careful, we need to add 2k pi. Okay, k is just an integer. And we need to do that, and you'll see why. If you don't do this, you'll see you'll only get one solution, and you'll see here z cubed, we need to get 3 solutions. And so it's up to you how you want to keep solving this. I'll show you how I do it, just so that I don't get confused. What I'll do is just put this over the same denominator. Okay, so I'll put it all over 2, and I'll have pi plus 4k pi. I just find that easier because this just feels, I don't make mistakes when I do this. If I don't do that, I make mistakes. Okay, so I've got 3 theta is equal to all of this. Okay, therefore theta is equal to, divide by 3, we get pi 4k plus 1 over 2. We're dividing by 3, so we get 6 there. Okay, so that's what my theta is equal to. Now let's just look at different values of k. If k is equal to 0, what do we get? If k is equal to 0, 0 plus 1, we get pi over 6. Okay, remember we're looking for values between negative pi and positive pi. So we've got pi on 6 at the moment. What happens if we do k is equal to 1? What do we get? We get 4 plus 1. We get, sorry, my brain just went. 4 plus 1, 5 pi over 6. Is that within our tolerable arguments? Yes, it is. So that's a tick. So that's fine. That's a tick there. Let's try k is equal to 2. K is equal to 2. We get 8 plus 1. So that'll be 9 pi over 6. No, that is too big. It's gone past pi. So that is not a solution. And so let's go backwards. Let's try k is equal to negative 1. And what happens when k is equal to negative 1? Negative 4 plus 1, negative 3 pi over 6, or negative pi over 2. Okay, and again, that is in our range. If we want k is equal to negative 2, that would go too far back this way. So it goes back past negative pi. So there are 3 solutions. So therefore, what are our 3 solutions? We have, now remember r, we've got r cis theta. So we've got 1, so z is equal to cis pi on 6 is our first solution. I'll just say 1, 2 and 3, there are 3 solutions. Z2 is cis 5 pi on 6, and the third solution cis negative pi on 2. There are 3 solutions, and they're all modulus 1, so there's 1 sitting in front of here, but we don't bother writing those, obviously. Okay, so there are 3 solutions, and there you go. And what you'll notice is if we put them, and I'll just quickly do it here, quickly do an Argand diagram, where are these things? Cis pi on 6, so that's roughly there. Okay, cis pi on 6. Cis 5 pi on 6 is there. Okay. And cis negative pi on 2 is there. Okay, so, and you'll see that all of those are equal distance apart from each other. They divide the circle into 3 pieces, and they all have the same modulus there. So there we go. That's how you do a cube root. Okay, so let's quickly do a square root. When I say quickly, I don't mean quickly. Okay, so let's find the square root of, let's say 1 plus root 3i. Okay, now there's 2 ways to do it. I'll do it 2 ways. I don't know if I'll fit this on the page. These problems take a lot. So, firstly, we'll do it the polar way. Over here, we'll do it the Cartesian way. See if I can fit it all in. Polar way. Let's convert this guy into a polar form. R is equal to the square root of 1 squared plus root 3 squared, and that's 2. And tan theta is equal to root 3 over 1, so that's root 3, which implies that theta will be, just a quick little sketch here, root 3 will be up here at pi on 3, and we're in the first quadrant because both 1 and root 3 are positive, and so that therefore we've got pi over 3. So therefore what we're trying to solve is the equation we want. Z squared is equal to 2 cis pi on 3. Okay, so what do? We let Z be r cis theta, Therefore, z squared, we've got r squared cis 2 theta is equal to 2 cis pi over 3. I'm going to run out of space. Therefore, equate the modulus. Therefore, r squared is equal to 2, which means r equals a root 2. R is always positive. And also, we have 2 theta is equal to pi over 3 plus 2k pi. I'll just write them over the same like I did before. Pi plus, if we write it all over 3, just multiply that by 3, 6k pi. And therefore, theta is equal to, take the pi out the front, and we've got 6k plus 1 over 6. Okay, and what do we get? Let's have a look. If k, oh, see, I've just crunched it up a bit too much. K is equal to 0. What happens when k is equal to 0? Then you get pi over 6. And if you get, so pi over 6, where is the other one going to come from? I know that if I go k is equal to 1, that's going to push it over the top. If k is equal to 1, you get 6 plus 1, 7. Pi and 6 is too big. So I know that I'm looking for k is equal to negative 1. And that'll be negative 6 plus 5, that's negative 5 pi over 6. So there's my 2. And so therefore, my two solutions are z1 is equal to, my first square root will be equal to, what was the modulus again? I've lost it. Root 2 cis pi over 6. Second solution, z2 equals root 2 cis negative, I did fit it in, there you go, over 6. Okay, there you go, there's the solutions. Now, I'll just check to see how much time I've got left. I might have to, I reckon I can finish it. Let's go, here we go. The other way to do it is using Cartesian. So what you do, what we're trying to solve is z squared is equal to 1 plus root 3i. What we're going to do is let z be equal to x plus yi. Let's just plug that in and equate coefficients and go. Okay, so therefore, x plus yi squared equals 1 plus root 3i. Therefore, expand this out, you get x squared plus 2xyi plus y squared I squared equals 1 plus root 3i. And just to simplify that, we've got x squared. Now this will be negative y squared because we've got that I squared there, plus 2xyi equals 1 plus root 3i, and I'll stop there. From here, you always get that as being the real part when you do this, and you always get that as being the imaginary part. So you don't actually need to do any of this work here when you're doing this, because you will just know that. And so what you get if you equate the real and coefficient, you'll always get x squared minus y squared being equal to the real part here, and you'll always get 2xy being equal to the imaginary part, root 3 there. And I'm not going to do it, but all you do is you do simultaneous equations. To solve this, I would do it on my CAS calculator. I could not be bothered, that's going to be a little bit messy. But put that into your CAS calculator and you'll get x equals something, y equals something. Hang on, I did it because when I was preparing for this video. So you solve those two equations and it spits out these values and you get your answer. Get your answer for x, your answer for y, and then you write z equals, whatever it was, root 6 over 2 minus root 2 over 2i, and the other one, z2 equals blah blah blah. And so you get the answer in rectangular form because you did it Cartesian. So they're the two ways you can do it, either in polar form like this or in Cartesian form. And that's how you find square roots. A little bit messy, but that's how you do it.